So today we start on week 7, which covers electric flux density, Gauss law, and and the application of Gauss law in probably solving the issue, the electric flux density for asymmetric media and asymmetric media. So that is where we're supposed to do today, and I hope in the afternoon we might cover this, which is electric potential, etc., for week 8. And on Friday we might cover the electric fields in materials. I'm trying to do examples in the midst of the lecture, but I'm also in touch with my GA to be sure to allow to do some tutorials, examples, and problems with you. And that means next week we might need to do Part 2 so that we are at par with our schedule. That might be next week on Friday, because I might cover this material on Tuesday. And if we do that after next week, then we shall only remain week 10 and week 11 and week 12. Week 12 is a bit debatable. I might actually give you some material to go through, but we shall be left with only week 10 and 11. So if we, in the next 2 weeks, we cover enough material, we might have finished our lecture and then only start with the revising, etc. So that's where we are. About the next class, we actually discuss later after this, but as a matter of fact, the timetable has given us this time. The one who is asking about the makeup cards, we will plan for a makeup card, don't worry. So yeah, I think now we can actually start off. So we are supposed to discuss on electric flux density, and as usual, I will stop the video just as per your request. And we now say that the electric flux due to electric fields can be calculated using general definition of flux as we found in equation 313. And this is the equation that we are referring to. We found out in one of our lectures that the flux, which is has a symbol psi, and actually in the beginning of the lecture I put some reminders of these symbols here. That this symbol we call it psi, and this other symbol, which we have not yet used, but in the past I have confused it myself. This symbol, we call it psi, or which sometimes when you are writing it in handwriting, you might have seen me writing it as such. So I'm saying that those symbols are important, and therefore I'm saying that we use this symbol psi to represent the flux that is passing through probably a surface or a volume, and we are saying that the general definition of the flux is defined in this equation 313 that I just brought it here for us to remember, that we said it is normally a factor of the vector that is crossing through a surface and then over that surface, the area over that surface. So then is the integral over the surface, or the surface integral that vector A is passing through. And therefore, our vector is now the one that we are going to generate, or to reformat our equation so that we can express the flux due to electrostatics through a medium. And we are now saying that this equation is not very useful, particularly when we want to, when we are expressing it in terms of electrostatic or electric field strength, or etc. So we are defining a new definition, or a new formula that can allow us to define electric flux density. They're saying that equation 411 and 416 show that the electric field intensity is dependent on the medium in which the charge is placed. That is equations that we might have found earlier, and I just brought one of them here. We say that electric field intensity is always given by q over 4 pi epsilon naught r squared, and the unit vector is expressed as such. And therefore, what this is saying is that the electric field strength is dependent on epsilon naught. The epsilon naught is the material medium, or the permittivity of free space. And therefore, if we are not dealing with the free space, the permittivity will change to include epsilon, or it will become epsilon naught, epsilon r, because now this is the one that determines the permittivity due to a medium that is not free space. We are saying that clearly from what we found from those equations, that electric field intensity or electric field strength is going to depend on the medium in which the charge is placed. And for that reason, we can just define a new field vector D that we give as expression 435. So we are just saying that we found out that E is dependent on epsilon naught, or permittivity of free space, and therefore if we define D as the product of that, then D stops being dependent on the medium, because now there is a factor already, it's already factored. And therefore, we are saying that equation 435 becomes a new definition for electric field. Oh, this term that we get after we have multiplied the permittivity of free space with the electric field strength, we get a new term that we are referring to as electric flux density. And we want to show some characteristics of that. We are saying now that from that equation we can define electric flux in terms of D, which we are expressing as this is something we have already said, that from equation 313 we said that flux was equals to A dot ds surface integral. But now we are saying that because we have expressed D as epsilon naught E, we can now replace A with this D. And that is why we are bringing this D at that point. So we are saying that that becomes our new expression of electric flux, just as it was defined in 313. And now we are saying that in SI units, one line of electric flux emanates from one coulomb. And therefore, what you actually find is that electric flux is given in the units of coulombs, which are the units of charge. And therefore, we are saying that if you have a charge Q, which is equal to 1 coulomb, it will generate one flux line, which again is expressed is equals to 1 coulomb. So we're saying that that is the equivalence. But you remember that we normally draw the positive charge as having lines that are coming from it. So we are saying that if it is only 1 coulomb, it will generate only one line of flux. And of course, we know on the reverse of that a negative charge terminates the flux lines. So if you actually remember how we represent, how we represent a positive charge and a negative charge, we always say that flux lines emanate from a positive charged body. So if this is a positive charged body, then the flux lines are coming out of that. We normally have, that is how we draw flux lines. But if it is negative, Q negative, we see that flux line terminates through into the negative charged body. So that is nothing new. I guess you already know that. So, but that goes without saying. Therefore, the electric flux is measured in coulombs, just as I have already mentioned. Hence, the vector field D that we have defined is now called electric flux density. We have just defined a new term that allows us to relate the electric field intensity that is dependent on the medium, now to get a term D that is now independent of the medium. And this D is measured in coulombs per square meter. And for historical reasons, the electric flux density is also called electric displacement. So what we just need to get to know here is, and to be very clear about, is that flux is the one that you are measuring in coulombs, but now D is measured in coulombs per meter squared. And therefore, as you can see, flux is going to be given by D times area, or that is why we are doing the integral of A of ds. So that should come out as clear. The flux is all the lines that are passing through the surface, of course, multiplied with the flux density. So from equation 435, it is apparent that all the formulas derived for E from Coulomb's law can be used in calculating D. So we are saying that all the formulas that we derived that were similar to this, because we talked about infinite line. If you remember, infinite line that is charged. So, and we developed a formula for that. And then we talked about finite line. We talked about infinite service. Infinite service. And we also talked about a finite volume. So we are saying that the formulas that we developed for calculating the electric field intensity for these services, we can still use those ones to get the electric flux density from the same formulas. That is what that statement is saying. And the only difference that we are saying is that if we get E, say for a line, then if you multiply with epsilon naught, because we are dealing with free space for now, then that gives you D. So I guess that is quite clear. So that is what this statement is saying, that from the equation 435, which we have just obtained here, which is right actually this one, then we can always get a D from E that we have already found out from those many equations that we developed. It is apparent that all the formulas derived for E from Coulomb's law can be used in calculating the D, except that we have to multiply those formulas by epsilon naught. For example, for an infinite sheet of charge, if you actually remember, and I guess I have brought it here, it must be somewhere that I put here. I'd copied that formula. I think I never did. I never copied it. But for an infinite sheet of charge, which we called a service, we said that I can probably clean my left. We said that E, I'm just trying to remind you what we already said. We say that electric field strength E is given by rho S or over 2 epsilon naught. That is actually how we found from the equations that we are referring to in section 4 and 2. But therefore, if you want to find D, we can always multiply by epsilon naught, multiply by epsilon naught, this epsilon naught goes, and this gives you a D. And this D is electric field strength, electric flux density. So of course, it's a vector. It has to have the AN. The AN is always points the perpendicular normal, the direction perpendicular to the surface that we are referring to. So, and for a volume charge distribution that we must obtain from these equations, we can always get as this. Remember that the volume charge distribution, we said that is simply going to be similar to like it is a charge, a unit, or that in a small charge or in infinitesimal charge, that we said that is going to be given by law V, which is the charge density or volume charge density over you integrate over the volume, and then we said that we takes the normal form of 4 pi epsilon naught r squared, and this has to be in the direction of AR. So if that be the case, and this was giving us E, then you can always multiply by epsilon naught, and you multiply by epsilon naught. This gives you a D, and as you can see, this epsilon naught cancels that, and therefore we are left with equation that is similar to equation 438. And what we now observe is that D is a function of charge, which is obtained by this, and position, which is obtained by this only. And that is what we said, that now D stops being, is no longer dependent on the medium on which the flux are flowing through. That is a very important parameter that we have just developed right there. So that serves as an introduction to electric flux density and how we can be able to get electric flux density from the formulas that we developed for electric field intensity. So, and that serves as I think sufficient introduction. And I purpose that we look at this example just to be sure that we can get to know the significance of D in line of or what it means in the context of free space. So here we are getting an example 4.7 that says that determine D at this point, determine D at 4.403 if there is a point charge negative 5 pi microcoulombs at this point 400 and a line charge 3 pi millicoulombs per meter along the y-axis. So of course this example has not actually it has drawn it for us, but I have tried to sketch it for us. And this is the diagram that I drew, which you can always compare with the one that the example has given us. So if you look at this, we have the y-axis, we have the x-axis, and we have the z-axis. And point, this is a sketch, therefore this that does not represent a real the diagram in scale. But for 0.400, where the charge Q1 is placed, can simply be sketched or placed along the x-axis because y is 0 and z is 0. But along the y-axis, the x-axis, that is 4 units. So you are moving from the origin towards towards the z x-axis, and you move 4 units. Then the 0.403, I figured out that it is still along this the x is equals to 4, but then you towards y you go 0 points, but then towards z you go 3 points, and therefore I place it at that point. And then what are we saying? We're saying that this is the charge, the first charge. This is the first charge that is going to act on this point. Our point 3, I actually labeled it point 3. Point 3 is our point of observation. And this is our first point that is going to cause the field brings up or to have some flux into electric field strength at point 3. The other point or the other source of the field is the charge placed along line Y. So we have two sources. One is Q1, and the other one is line Y, which is, as you can see from our diagram, it just describes that there's a line charge, 3 pi millicoulombs per meter that is placed along that line, and our charge that is placed at 400 is minus 5 pi millicoulombs. So this point of observation, which is I'm calling point 3, is receiving effect from this and that. So we just treat them individually and then apply the superposition theorem or superposition law that we said applies for charges to get the total charge or the total field due to, or the total flux due to these two sources of charge. So we start with dq. The dq is the one due to q1, and I just did some quick expressions here, and I said that d, or the electric flux density due to charge q1, is going to be epsilon naught multiplied by epsilon 1. This is not clear. I can clear it. I can make it a bit clearer. This is supposed to be 1, 3, which says that we are observing the electric field at point 3, it is due to 1. So, and of course, we know that Q1, this is Q1. The formula for E is 4 pi epsilon naught, which was there. So if you multiply with epsilon naught, this of course cancels. And then you are left with Q1, 4 pi r squared. Then the direction is R13. Before we even plug in the values, we have to find the values of AR3 and R squared. Of course, this is supposed to be magnitude of R13 squared. So we start with that point and we say that AR13, which is the unit vector along direction R13, is simply going to be found from R13 divided by the magnitude of R13. And before we now get this, before we even figure this out, we are going to find R13, which is the R at 1 minus the R, sorry, the R at 3. This is R at 3 minus R at 1. So in case you might have forgotten how we do that, we said R at 3 is 403. Then you minus R at 1, which is, or when I say R at 1, I'm not talking about the position vector R1. So you minus 400, which is this one. So that gives you 4 minus 4 becomes 0, 0, 0 becomes 0, and 3 minus 0 becomes 4. This is actually becomes 3, which is along the AZ, because the AX and AY of course have 0 elements. So that's why you have 3AZ. But then if you are now to find the R13, which I think I never did because I took it for granted, we have seen that R13 is equals to 3. So we just need to say 3 squared square root, and therefore this gives you a 3. And that is why where we are now saying that this becomes 3AZ divided by 3, and this gives you our unit AZ. So therefore our AR13 is equals to AZ hat, which is the unit vector. And therefore, now coming back to this equation, we can just plug in the values. We were given that Q1 is equal to minus 5 pi millicoulombs, that is 10 power minus 3. And of course, our epsilon went, therefore you are left with 4 pi over R, which is 3, and then you square, of course, as per the formula, and then you put your unit vector right there. And we are going to be, this gives us this value right here, which is minus 1, 0. Of course, when you do this calculation, this becomes straightforward, becomes 0 minus 0.139 in the direction of Z. And of course, I just went along a route, and you can see that that is the same answer that we got here. This is in millicoulombs per meter squared. As I have mentioned, that solution gives us the electric flux density dq due to the point charge q. And therefore, we can also now try to find the electric flux density dl due to the line that is placed along the y-axis. And all you have to remember is what we have said, that we found out that electric flux density, electric flux density due to a line charge is, we obtained it from the section that we referred to, 4.2 and 4.3. We found out it to be equal to rho L over 2 pi epsilon naught rho. That is how we found this is due to an infinite line that, of course, that is charged, an infinite line. This is how we found out that it is to be. Therefore, if we are to obtain the electric flux density due to an infinite line, you simply multiply with epsilon naught, and you multiply with epsilon naught, and this goes. So nothing strange there. We are just using a formula that we have already developed in the past. So we end up with this formula right there. And we are now saying that, of course, in the direction of A rho, because we said that it's a line that is going to, and the field is going to be pointed towards the radial direction of the line, and the radial direction is A rho. So once we know that, then we can always come here and say that what I've just shown you, that is now epsilon naught times E23. And when I say 23, I'm saying that the field strength is pointing from 2 towards 3. And clearly you can see that we are using that formula, rho over 2 pi rho. Then the new item that you need to actually to evaluate is the unit vector and the radial distance, which is rho. But therefore, before we plug in these values right there, we need to evaluate this item and R or rho. And of course, as a matter of fact, we can always be able to get this one. And the R23 is obtained from R3, that is the position vector going from the origin towards 3, and the position vector of charge of the point of, the point of observation, and this is the point of where the charge or the field is emanating. And therefore what I need, I guess that all of us should be cautious about is how I'm getting this point. Because this, we know the point of observation is 403, that's a fact, but it may not be straightforward how we are getting 0.403. And at that point, I would actually take you back to the diagram and tell you this, that when you're observing the field due to a line or an infinite line that is charged, you always get the point. You always look for the point that is perpendicular to your point of observation. And in this case, we can see that we are told that this line still just lies on y. And therefore, we just needed to find a perpendicular line from our point of observation to the source or to our infinite line. Therefore, you can actually, if you do proper sketching, you actually find out that if my point of observation is at 0.403, the most important item to look at is this, because when you are told that this is a y plane, a y line, you always know that the x is equal to 0